Hi everyone. Welcome back to the training series. In the previous part, we simulated the flow around a ship propeller blade using MRF. Then we compared our numerical results at different inlet speeds with experimental test data. Overall, our workflow was import the mesh, convert the mesh into a part, convert it into regions, define physics, and enable MRF. In this part, we want to look at the flow field a bit more closely. So let me start by creating a new empty scene. Now select Boundaries. From the rotating region, select Blade and Hub. Put those boundaries into one surface selection. Then from the static region, select the shaft boundary and add it to the same surface. Click OK to create the new surface, then go find the scene you created. Here's the scene. Now I'll rename it. I'll call it Cavitation-Risk. In this scene, I want to check where cavitation is likely to form on the propeller. If you're not familiar with cavitation, when a propeller works underwater, local pressure can drop below vapor pressure. And vapor bubbles form and collapse, like in this video. Many times, when a propeller operates underwater, you get strong pressure gradients. In some locations, pressure drops below vapor pressure, like at the blade tip vortex. At that point, water changes from liquid phase to vapor. This phenomenon is called cavitation, and it comes with noise and erosion. So in many design applications, you should do a risk analysis to avoid cavitation. In this scene, we want to do that. First, let me adjust the colors I use in this scene. I start by setting a constant surface color, and I choose a color that is commonly used for blades, something like this orange tone. Next, I want to create a pressure ISO surface. So in Derived Parts, right-click, New, and choose ISO Surface. Make sure all regions are selected. For the scalar, select Pressure. You could also use Pressure Coefficient, but I'll stay with Pressure. When you select Pressure, it shows a default range down here. If you click Query, STAR-CCM Plus calculates the pressure range in the selected region. It tells you what values this pressure field takes in that region. Now I want to add this ISO surface as a new surface display in this scene. So I click Create. Then I click Close. OK. Now I rotate the view a little. This is the location of my ISO surface for the current threshold. The blue regions you see are low-pressure zones, where cavitation is likely to form. So in this condition, we may have root cavitation and also cavitation near the leading edge. Now we can do one more thing. We can change the ISO surface pressure value. And if you look again, you can see where low pressure may appear. You can play with this value and test different thresholds. A useful threshold is the saturation pressure, meaning vapor pressure. For this case, it is about 2,340 pascals. You can see cavitation risk on the hub and on the blade. And then you compare these patterns with experimental measurements. In my example, the mesh near the tip vortex is too coarse, so I cannot capture it. I only capture bubble cavitation on the blade, and it appears like this in the steady solution. Okay, now you can explore your results. Create different plots and move forward. Another thing I want to do now is to change the motion model we are using. In our current example, we used MRF. So we modeled rotation without physically moving the blade. Now we can do the opposite for motion. We can use a real motion model, like rigid body motion. So I add a rotation motion here, and I rename it rigid body motion. So it is clear this is rigid body motion. I'll call it RBM, which is short for rigid body motion. Now, if you compare it with the previous rotation, we need to apply the exact same parameters. Set the rotation rate. The rotation rate should be 15 RPs. And I copy the axis direction exactly. The axis is correct, and the origin is at 0, 0, 0. We do not need any other parameters, so everything is copied from the MRF setup. Now that RBM is created, go back to regions. Find the region and open physics values, motion specification. Here I switch the frame back to reference frame. And the motion is currently stationary. But before we change motion here, we need to change the physics model. Right now our continuum is steady. So we need to switch it to unsteady. Then I return to motion specification. Now you can see, after switching to unsteady, I can select the proper motion model. In steady mode, you cannot move the body. So RBM is disabled there, but in unsteady it becomes available automatically. Now I apply the motion specification here. Another thing I could change is solver settings, but I'll leave them as is. Now let me advance one step. Now I go back to the cavitation-risk scene. Let me disable the pressure ISO surface and set the view in +X with Y up, looking at the blade. Then I change the projection mode to parallel. Okay, this is the blade. Now I apply rotation. In many industrial problems, when the mesh count is very large, if we only need forces like thrust, torque, and efficiency, it is okay to start with a steady run. But if we really want to study cavitation or match the blade behavior more accurately and compare with experiment videos, then we should run it with rigid body motion. Okay, let me stop the run now. Let's go back to our cavitation-risk scene. Now let's add the blade surface to a pressure scalar display. I select blade and hub, and I add them to the scalar display. The scalar I choose is pressure, then I click OK. Now this gives us the visualization I want. Now that the view is clean and it shows pressure values, we can click Run. I'll let the solver continue. Then we come back and continue the discussion. With this part of the exercise, this chapter is now close to the end. I will prepare one more final part, the final section of motion modeling in STAR-CCM+. There will cover a few extra technical tips and details that should be mentioned more clearly. For example, I'd like to discuss how different motion regions can use different physics continua. We'll go into that, review the key technical points together, and I'll see you in the next video. Good luck!